Good morning, everyone. So today we're just going to go over a little bit of a review of Calc 1, and more importantly, we're really going to be focusing on integration. But before we do any of that, the big question should be, well, where do I find some of this information at? So what I'm going to do is I'm going to go ahead and show you where this is. So let's go ahead and let's go here to Blackboard, and you can see our course right here. It's going to be Calculus 2. It should have this nice little waterfall thing. I did not pick the picture. It picks it for me. I guess I could update that if I wanted to, but I'm going to leave it like that for now because I kind of dig it. So we're going to click on here, and I'm just going to put it in, well, I'm going to leave it like this. This is fine. So obviously right here are the announcements. There's no announcements yet as at the recording of this video, all right? But on the left-hand side here, you're going to see important forms and cheat sheets. So I think this is going to be really important here. I'm going to be building this as the semester progresses. But right now, I uploaded a bunch of little cheat sheets that I did not create. So I want to give full credit to Paul Dawkins, who is a phenomenal calculus professor, and actually he's created these amazing documents for us. So we're going to go ahead and use them. But real quick, just to show you, here is the algebra one that you can print up, and it kind of just goes over all the basic things for algebra, like properties of the absolute value, factoring formulas, completing the square technique, things like that. But the one that we're really going to want to look at here, and there's actually three of them. The calculus cheat sheet all is basically the derivatives, the integrals, and the limits. All of this in the middle all together. It's 11 pages. All right. So if you want to, you can click on here and you can print this one up if you want. All right. Nothing wrong with that. But there's also, I broke them up into like little individual ones. So let's go ahead and let's look at the integrals. All right. Now, the hard part about teaching an online class where there's a lot of transfer students, meaning like in the summer, is the fact that I don't know what type of calculus you have walking into the class. So like, for example, if I scroll down a little bit at our common, or with looking at our common integrals here, there are some people that went ahead and figured out or learned what the integral of e to the u du is, all right? Versus there's some of us who don't. In other words, in Calc 1, some people go over e to the u. Some people don't. Also, we should all have familiarity with the integral of of our trigonometric functions, but sometimes we don't go over some of the hyperbolic functions, which are down here a little bit lower. All right. Also, in Calc 1, some people go over integration by parts, some people don't. So I'm going to approach this as if you've never seen this stuff before. All right. So in the tutorial videos as we progress throughout the semester, if you start seeing me going over like e to the u and you already know how to integrate that, by all means go ahead and fast forward a little bit, save yourself some time, or watch it to review. So what I'd like to do now is I just want to go over some basic integrals, and then we'll progress using this table right here. This is not going to be a huge long video, but there's going to be a lot of examples here, for us to use. So let's go ahead, let's change it over to here. And the first thing I want to go over is a review of the power rule. So we want to integrate the square root of x dx. Now, the power rule, if you remember, and you can look this up on that cheat sheet, is the integral of x to the n dx is going to equal 1 over n plus 1 x to the n plus 1 plus c. And there is a very special restriction. N is not allowed to equal -1. We'll go over that in a little bit. So the issue with the problem that we have here is, although I have this beautiful function of x right here, this square root of x, it is not in a proper form for me to apply the power rule. So what I'm going to have to do here is do some algebra first. I'm going to have to rewrite this as x to the 1/2 dx. Now that I have the integral of x to the 1/2 dx, I can go ahead and apply my power rule. And for this first one, I'm really going to write it out. It's going to be 1 over 1/2 plus 1, x to the 1/2 plus 1, plus an arbitrary constant. And then just using some basic algebra here, we get 1 over 3 over 2, x to the 3 over 2 plus c. And finally, to simplify the coefficient, it's going to be 2/3 x to the 3 over 2 plus c. And that's it. So that's really what I'm looking for. And like I said, with this first one, I really wanted to demonstrate basically how to use our product rule there, only because the table of integrals really helps out. All right. And eventually we're going to reach a point where we're going to have to really lean on them to kind of just simplify all of the other stuff that we have going on. So let's look at another example here. Now this one I'm going to go a little bit faster. So we have the integral of 1 over x to the second dx. Now once again, I'd love to use the power rule, but I can't. So I'm going to have to algebraically manipulate this to make it x to the negative 2 dx. That is the negative exponent rule from algebra. And now when I go ahead and apply my power rule to this, remember, I'm going to add 1 to the exponent and divide by that as well. So 1 over negative 2 plus 1, x to the negative 2 plus 1 plus c, and that's going to equal negative x to the negative 1 plus c. So for the next example here, we're going to go ahead and we're going to start looking at definite integrals. All right, now the ones that we did previously, let me highlight the answers here because we can see them on the board. So just recall that these are called indefinite integrals, and that is because we are missing the limits of integration, which that right there would be our upper limit. Down here, this would be our lower limit. And since we do not have these, we call this an indefinite limit, which basically what ends up happening is the solutions that we arrived at, like the negative x to the negative 1 plus c, which we can actually rewrite that as negative 1 over x plus c. The plus c part provides us with what we call a family of integral solutions. So what ends up happening here is whatever that c happens to be will give you a different answer. That's why with indefinite integrals, we say that there are almost limitless answers. And that is because we have no idea where that plus c actually is living, okay? Conversely, with a problem like this, we have the integral, and this is a very nice easy one. We have the integral from negative 5 to 5 of pi dx. Now, with this problem, first things first, we got to remember pi is a constant, all right? It is a constant value. So the formula that we're going to be using is the integral of k dx is equal to kx plus c. That's the formula that we're going to be using. So the integral of pi dx from negative 5 to positive 5 is going to equal pi times x, but now we're going to evaluate this between negative 5 and 5. Now visually, here's what's happening. Right here in red, okay, the red line going across, that is the graph of y equals pi. That is a horizontal line with the y-intercept 0, pi. The shaded region represents the area that we're trying to find. So we're trying to find from negative 5 to positive 5, okay? So to do this, all we're going to do is evaluate the antiderivative that we came up with, pi x. So we're going to get pi times 5 minus pi times negative 5. Now the thing to remember here is that we evaluate the upper limit, and then we subtract the lower limit from that. All right? So what we end up getting is 5 pi, excuse me, 5 pi plus 5 pi, which is equal to 10 pi. So this is what we call an exact answer, which is extremely important for us because 99% of the time when we're doing our homework or a quiz or something or an exam, we want exact answers. So 10 pi. But this is approximately 31.4 rounded to the nearest tenth of a decimal. And this is good enough if the problem says, hey, round to the nearest decimal place, like the nearest tenth or the nearest hundredth or thousandth or something like that. And just to verify this, if we go back here into our picture, I can open up my side screen, and we can see here that we get, and hopefully you can see my mouse on the left-hand side, we approximately get 31.4159 and all that other decimal stuff underneath there. So this is what we call evaluating a definite integral, and we did it with using the constant rule. So now what we're going to do is we're going to go ahead and start stepping up the difficulty here. So now let's look at this one. We're going to look at the integral from 1 to 4 of 2 plus x squared all over the square root of x dx. Now, sometimes we just can't look at that nice chart that we have, that cheat sheet, and we can easily identify the integral that we're using. Sometimes we actually have to step it up a little bit, and we have to algebraically manipulate the function f of x that we're trying to integrate. All right? So highlighted in blue is what we're going to have to algebraically manipulate to form it or conform it into something that we can use. So the first thing I'm going to do here is I'm going to go ahead and just separate my numerator. And the reason why I'm allowed to do this is because I have a monomial in my denominator. So because the square root of x is a monomial, I'm going to go ahead and just separate them. Now, I'm just going to apply some rules for exponents here to rewrite it. So I get the integral from 1 to 4 of 2x to the negative 1/2 plus x to the 3 over 2 dx. Now, really quick, for those who kind of don't see what I did with this, especially with x to the 3/2, all I did is I took x to the second over x to the 1/2, and oops, that looks kind of bad. X to the 1/2. I noticed that the bases are the same, and I'm dividing, so it's going to be x to the second minus 1/2, and then I just found a common denominator and simplified to give me x to the 3 over 2. That's all I did there. All right? So let me go ahead and erase this real quick, because now I have it in a form that I can go ahead and I can integrate this. So after I integrate this, I'm going to get 4 x to the 1/2 plus 2 over 5 x to the 5 over 2. And we're going to evaluate this entire function between 1 and 4. All right? So hopefully you're following along with me. If not, you could pause the video and go back. But all I'm going to do here is just go ahead and make my substitution. So I get 4 times 4 to the 1/2 plus 2 over 5 times 4 to the 5 over 2. This is my upper limit. I'll put it in parentheses because we're going to subtract away the lower limit. So this right here is going to be our lower limit. So just go ahead and make the substitutions. We got 4 times 1 to the 1/2 plus 2 over 5 times 1 to the 5 over 2. Oops. There we go. Sorry about that. And then just to simplify it a little bit further, we end up with 8 plus 64 over 5 minus 4 plus 2 over 5. And when you find a common denominator, you simplify everything. You end up getting 82 over 5 for a final result. Now, there is one thing that I want to show you, because I know a lot of us have these calculators, and to be completely honest with you, this is Calc 2, so I'm assuming that you know how to do fractions, but really what I want to show you is I just want to make this a little bit simpler on us. So I'm going to open up my calculator here. Give me a second. Let me put it in the detached LCD screen so you can actually see what I am typing. Let's see. Can I make this a little bit larger? There you go. I think that's good enough. So let's clear this out. And really what I'm trying to show you here is this. If you wanted to, you can take out your calculator and type this in as parenthesis. So we're going to do the quantity first. 8 plus 64 over 5 minus the quantity 4 plus 2 over 5. Now, before we hit enter, we're going to go ahead and hit the math button first. We're going to scroll down. Well, actually, it's already selected, so hopefully you can see where my mouse is. It says option number 1, arrow frac. What that means is give me my answer in a fraction, please. So we're just going to click that once and then hit enter one more time, and it gives you 82 over 5. So I don't know if some of us knew that your calculator could do this. If you have one of the really fancy new TI-84 calculators, all right, when you hit the math button, you're going to see math, number, complex, probability, and then there's a fifth option to the right that you can't see on this calculator that I have, because this is, let's be honest, it's a pirated one from the internet that I found. But it'll say frac, and then underneath that it'll have pictures of fractions, and then you could just type it in exactly how you wrote it, which is extremely powerful. So let's go back here real quick. Oops. Quit, please. There we go. So 82 over 5 is our result. Now, 82 over 5 as a decimal for an approximate answer is going to be 16.4, which is very nice. And what I want to do is go ahead and show you what we're doing here visually as well. And I will end up copying and pasting this into this lecture, because I think it's going to look really pretty. So the function that we're really concerned with is 2 plus x to the second all over the square root of x. And we want to evaluate this between 1 and 4. So we're gonna our lower limit is 1, our upper limit is 4. And notice here on the left, or right above, we get the approximate answer, 16.4. And what's really nice about this is here we can see exactly what we're trying to integrate. Zoomed out way too much there. Let's see, I guess that looks good enough. So we're just integrating that shaded region right there. So I'm going to go ahead and copy and paste this here into our notes. Because yes, you will end up having access to all of my notes and everything like that once I upload them. So do like a nice little picture here, and there we go. Oh, let's put it right there. I like that a lot more. All right. So how about we do another problem? All right, so for this one, we're going to integrate. It's a huge integration sign. Let's shorten that up a little bit. So we're going to integrate from pi over 6 to pi over 2, cosecant t, cotangent t, dt. Now, before we get real nervous, because I realize these are trig functions, all right? The first thing you always want to kind of do is you want to go back and you want to look at and see if it's one of those on our cheat sheet. So let's look at our cheat sheet real quick. So here's our cheat sheet, and as you can see right here in the middle, we have the integral of cosecant u, cotangent u equals negative cosecant u plus c. So right here, we don't have to worry about doing any crazy trigonometric substitutions or anything like that. And all we did is we took our time, we relaxed for a second, and we said, is this on our common integrals? Which I do put these on homeworks and quizzes and exams and everything because I want you to use this stuff. All right? So because we know the answer is negative cosecant u, we're going to go back into our notes. And we're just going to say, okay, well, this is going to equal negative cosecant t. And we're going to evaluate this between pi over 6 and pi over 2. So when we make our substitutions, this is going to give us negative cosecant of pi over 2 minus the negative cosecant of pi over 6. And just to clean this up a little bit, it's the negative cosecant of pi over 2 plus the cosecant of pi over 6. And using our unit circle, we can figure out exactly what those are. The negative cosecant of pi over 6 is going to be negative 1. The negative cosecant of pi over 6 is going to be positive 2. And negative 1 plus 2 is positive 1. Now, the thing that we have to remember is anytime we do integrals, okay, that is giving us the net area, all right? This next example here really demonstrates what's happening here, okay? So if I wanted to, let's say I wanted to integrate from pi over 6 to 2 pi of cosine x dx, all right? Now, if we wanted to integrate this, we could just look at our table real fast. We're going to go ahead and get the sine of x. And remember, we're going to have to evaluate this between pi over 6 to 2 pi, all right? And if we just go ahead and evaluate sine of 2 pi minus, the sine of pi over 6, we end up getting just 0 minus 1/2, which is negative 1/2. All right? So the thing, or something should be ringing off in your head, which is kind of like, well, first and foremost, if we're finding the area under the curve, how can you have a negative area? Well, the answer is you can have a negative area, but when we find the area, all right, we are finding a net change. We're finding that net area underneath the curve. So let me demonstrate what I mean here, okay? So if I just went ahead and typed in the cosine of x, and remember, we're evaluating this between, what was it again? I forget. Pi over 6 and 2 pi. All right. Let me get rid of this stuff so we can actually see this. We'll zoom in so it's nice and pretty. See, here's the issue here, okay? And I'm going to copy and paste this into our notes because I'd like to write on this. All right. So here's the problem. When we are evaluating from pi over 6 all the way over here to 2 pi, the thing we got to remember is you have area above the x-axis, so it's the area above the curve for that first region. We'll call this region 1. And in region 3, you have area above it as well. In region 2, you have area under the curve. So what's actually happening here is you are finding the areas in each region. It's just you're adding the two region 1 and 3 together, and you're subtracting the area from region 2 out. And that's why we're ending up with the integral of pi over 6 to 2 pi of cosine of x dx equaling negative 1/2. This is an entirely different question than if I said, find the total area for the integral of pi over 6 to 2 pi of the cosine of x dx. All right? See, total area, total area is really telling us, go ahead and find the area for region 1. Go ahead and find the area for region 2. Go ahead and find the area for region 3. So, we want region 1 plus region 2 plus region 3. So this is 3 separate problems here. All right? It really is. It's 3 separate problems. So you got to be careful when you are reading these questions. If it just says, integrate, whatever from pi over 6 to 2 pi of cosine of x dx, just integrate it, call it a day, whatever you get, that's what you get. But if you see these words, total area, then what we're going to have to do here is we're going to have to create 3 separate integrals. The first integral is going to go from pi over 6 to pi over 2. So this right here is going to be our first integral. All right, we'll just call it integral number 1. Then the second integral is pi over 2, 3 pi over 2. This is our integral for the second region. And finally, the third integral is going to be from 3 pi over 2 to 2 pi. So there is a difference in the way that we word these questions. All right. I'm going to leave that up to you to kind of figure this one out. It's just 3, little small ones. You'll be fine with it. But if you're interested in how I got pi over 2 and 3 pi over 2, there are 2 ways to do that. Unit circles the first. The other way is to just go ahead and hold on one second. I'm going to save this because I like it. The other way is just to just type in cosine of x. Oops, little typo there. Cosine of x. And just go ahead and say, okay, well, where does the cosine equal 0? And that's going to be at pi over 2 and then 3 pi over 2. Which, once again, if you just looked at your unit circle, you would find those as well. All right, so we're going to change gears a little bit here. We're still in the integration land. But this, for the majority of Calc 1 students, this is kind of like where you almost ended the semester. We're going to do a couple problems that involve U substitution. So just to remember here, we're going to go back. We're going to look at our table. So this is where you really started to talk about standard integration techniques, all right? Everything that we did before was kind of like a rule. Now we're using techniques, all right, which is entirely different. So in order for us to use U substitution, all right, and this is just A to B is just, what Paul did here is just kind of like said, okay, I'm going to give the most general case for everything. But what you need to have for U substitution is you need to have a composite function. That's this right here. That's f of g of x. In fact, you know what I'm going to do? I'm just going to go ahead and write this in our notes real quick. You cannot see what I'm writing. I'm just going to copy this down. F of x. Okay, there we go. Because I can go ahead and use my highlighter for things. All right, so here we go. So first, right here is our composite function. All right? That's f of g of x. All right? It's a function within a function. Now, in order for us to use U substitution, the way that we think about this is we got to kind of have some criteria that we have to meet. All right? First, you got to have a composite function and the inside function of the composite. You need to have its derivative. All right? So I think a really, really simple example of looking at something like this, all right, and I'm going to write it directly underneath, okay? Would be something like, let me see here. Let me find a nice one here. The integral of x times the square root of x plus 2 dx. Okay? You know what? I don't know if I like this example. Let's look at another example. I want more of a way more difficult one. Sorry, I'm like scanning through my notes real fast, trying to find like a good one. Let's see here. All right, I like this one more. Sorry. Let's do the sine of t times the square root of 1 plus cosine t dt. All right? Now, once again, like I said, this one looks very complicated, but I think it's a really good example to demonstrate what I'm trying to show. So first, right here is our composite function, okay? It is 1 plus cosine t, and then you take the square root of it. In other words, if you knew what t was, you would go ahead and evaluate 1 plus cosine t first, and then you would go ahead and take the square root of that number. That is a composite function in and of itself right there. In fact, if I broke this down a little bit, okay, the inside function here would be 1 plus cosine of t. All right, and then the outside function would be the square root. So sometimes when we learn about composite functions, sometimes people use like boxes, and what we call them are function machines. I guess I'm using the wrong variable here. Let's make it a t. My bad. So the first machine would be g of t. This would be 1 plus the cosine of t. All right. So if I put t into this conveyor line, right, into this machine going from left to right, the t would fall into that spot. The first machine would tell you, okay, thank you for giving me the letter t. I'm going to give you 1 plus cosine of t. But then you're going to take that result and substitute it into the second machine, which is f of g of t. So it takes the result of g of t and just puts it underneath that square root. And it just spits out the square root of 1 plus cosine of t. And that's it. Okay? So this is how composite functions work. You evaluate the inside or the first function, then you use that to evaluate the second function. All right? Going back up, I said in order for you to use U substitution, you got to have a composite function, check. But you also need the composite or the inside function's derivative. So I'm going to tell you this is what it is right here. All right? But now what I'm going to do is I'm going to demonstrate how do we actually check that. So if you remember, this is where your previous Calc 1 professor would say, okay, we're going to use U substitution. So we got to let U equal something. So you let U equal the inside composite function. That's going to be 1 plus the cosine of t. Then you take the derivative of that. So we kind of use like an abbreviated notation. We're going to say du equals, and all you do is take the derivative of the inside composite function. Remember, everyone, I'm going to use green right here. This right here is the inside composite function. All right, so that's this thing right here on the left-hand side. So when I go ahead and take the derivative of 1, which is a constant, is 0. The derivative of cosine of t is negative sine t dt. All right, that's what it is. That is a chain rule that I applied there. All right. Now, I had a in my humble opinion, an amazing Calc 1 professor when I was an undergrad. And one of the things that he taught me was always make sure that you solve the DU for whatever you're looking for. All right. And what I mean is this. Over here in our problem, that is positive sine of t. Now, what we have on the right side, right here, right side, so you can see I'm underlining it, that is negative sine of t dt. So what I'm going to do is I'm just going to go ahead and divide both sides by -1. In other words, I'm going to divide both sides by that coefficient of sine t. And I only do that because, and I'll show you here in a second, I only do this because I want sine of t dt, which is in the original problem, to match exactly what I have on the right-hand side of my u substitution. So in purple or lilac, I think that's a lilac color, you can see that, yes, we exactly match everything that we need. All right? So we have a composite function and we have its derivative staring us in the face. And once you can verify that you have those things, you are allowed to use u substitution. So the formula for u substitution, just to finish it all the way up above, the formula would be the integral of g of a, g of b, of f of u du. All right, that is what we're talking about here. So what I can do with our example is apply that formula. So I'm just going to scroll up here a little bit. Sorry. I'm going to scroll up here a little bit. And we're going to say, okay, because we've met the conditions up here. So let me clean this up there because there's a lot of writing here. I want to clean all this up. There we go. Let's clean that up, clean that up, clean that up. All right. So because we've met the conditions of a composite function and its derivative, we're going to go ahead and use u substitution. So wherever I see 1 plus cosine of t, wherever I see this, I'm going to replace it with the letter u. And wherever I see sine of t dt, which I'll highlight it here and here, I am no longer going to write that. I'm going to write -1 times du. So I make this substitution right there. That's all I'm going to do. And remember, the commutative property of multiplication says order doesn't matter when you multiply. Remember, 2 times 3 is the same thing as 3 times 2. So I'm allowed to put this -1 out front of the square root of u and put the du to the right. And there's u substitution of all of its glory. That's what it does. It takes a composite function and its inside derivative and converts it into a simpler function that we can integrate. So I'm just going to go ahead, pull the constant out front, rewrite this as u to the 1/2 du. And now when I integrate this, I'm going to write the answer down here, -2/3 u to the 3/2 plus c. And finally, wherever I see the letter u, I'm going to replace it with my original function, 1 plus cosine of t, all raised to the 3/2 plus c. And there's our answer there. Now, one more problem that I'm going to do is another u substitution, except I'm going to scroll up. I'm going to talk about these right here. Like, why did I write g of a and g of b? I'm going to show you where that comes from, okay? So give me a second here. I'm going to clean this up. All right, so here's the last problem we're going to do. And it is the integral from 0 to 13 of dx over the cube root of the quantity 1 plus 2x squared. Hopefully you're sitting there looking at this going, that looks crazy. And I agree. This although it's not a difficult problem, it looks crazy to begin with. But like I said, the thing to remember here is when the problems start to look a little bit crazier, okay, you're going to want to start thinking about techniques of integration, use substitution. So in our denominator, hopefully you can verify or you can see that we have a composite function, all right? So the big question becomes this. If we have a composite function, do we have its derivative left over somewhere inside the problem? Because if we do, then we can go ahead and we can use substitution. So the first thing I'm going to do here, all right, is I got to let u equal something. So remember, we let u equal the inside composite function. So we're going to let u equal 1 plus 2x. That's the inside, the innermost composite function. Now, du is going to equal, well, the derivative of 1 is 0, and the derivative of 2 using the chain rule is going to be 2 dx. Okay? So remember, I am a huge fan of just solving the du so there's no coefficients on the right-hand side. Like, I don't want this right there. And you'll see why in a second. So I'm going to divide both sides by 2. That reduces the 2 over 2. So the only thing I am looking for in my problem is, do I have a dx? And the answer to that question is absolutely. It's right there. All right? And notice, more importantly, all right, this is dx over 1. And I can take our problem and rewrite this as 0, or the integral from 0 to 13 of 1 over the cube root of the quantity 1 plus 2x squared times dx over 1. Like, you're allowed to do that, okay? So, do I meet the criteria for use substitution? Absolutely. Like, I am a very happy person right now, okay? So, here's what we're going to do. We're going to take our time with this, all right? Now that I know I can use substitution, I'm going to write an integral sign, and I'm going to make my substitutions. So 1 over the cube root of, remember, wherever you see 1 plus 2x, it is now going to be u raised to the second power. That dx turns into 1/2 du. And just to clean this up just a little bit further, I'm going to take this 1/2 and I'm just going to put it out front. All right, so that's looking pretty good. But the big question becomes, what do I do with the limits of integration? And the answer is, you have two options. All right? Option 1, you would just go ahead, you would integrate this, you would then convert back into x, just like we did up here. Let me show you. So in this example here, in our previous example, we converted to u, okay? We integrated, and then we converted it back into the variable t, which is what we were defining our variable to be in that situation, all right? So option 1 is to just do it exactly like that. Substitute original variable. All right, you could totally do that if you want. Option 2, change your limits of integration. So change your limits. So what I'm going to do is I'm going to change the limits. And this is where that definition from up above actually comes back into play here. So let me go back to our notes here. This is where this thing on the far right-hand side of your screen is kicking in. Let me zoom in a little bit more. All right, I try to make all my recordings in 4K, but I want to make sure that you can see this. There we go. That's where this is kicking in. The integral of g of a to g of b of f of u du. So the g of a and g of b, all that's telling you here is this. We are going to take, let me erase this stuff. We're going to take what we defined as u, which is right here. All right? And we're going to make the substitution of the limits of integration in for x. And then we're going to redefine what our limits are in terms of u. So for our lower limit, g of u is going to be 1 plus 2 times 0, which is equal to 1. So my lower limit goes from 0 in the variable x and turns into 1 for the variable u, because we're defining u substitution. The upper limit, and hopefully you can see this now, the upper limit is going to be, I'm just going to write an arrow, 1 plus 2 times 13, which is 27. So I'm going to go ahead and use 27 for my upper limit. So now what's nice about this is once I integrate this function right here, I don't have to go back into x. And the reason I changed my limits of integration to be defined by the variable u now. All right? So let's go ahead and let's just finish this problem out. We'll call it a day from here. So we got 1/2 times the integral from 1 to 27. And I'm going to clean that up because, once again, I want to make sure that I can go ahead and integrate this using some basic rule that I have. So to clean this up, remember, this is 1 over u to the 2/3 power du, which turns into 1/2 times the integral from 1 to 27 of u to the negative 2/3 du. And when you integrate that, you're going to get 1/2 times 2/3 u to the 3/2 sorry, typo. Hopefully you're all with me. It's not, it's 1/2 times 3u to the 1/3. My bad. Mental math definitely failed me at that time. The reason is I'm moving too fast. I don't want this video to be longer than 50 minutes. So sorry about that. And we're going to evaluate this between 1 and 27. So we just get 1/2 times the quantity, 3 times 27 to the 1/3 power minus 3 times 1 to the 1/3 power. And that turns out to be 1/2 times 3 minus 1, which is 3. Again, I am failing miserably with mental math today. We need to do this again. So we get 1/2. You know what? I am going to use my calculator here. I'm sorry. I thought I could do it in my brain. Obviously, I can't. So 27 to the 1/3 is 3. And that's going to be 3. So then we get 1/2 times 3 times 3 is 9 minus 3, and there's the mistake. So we get 1/2 times 6, which equals 3. There it is. So sorry about the little hiccups at the very end. You will notice that I am not perfect, but I definitely fix my mistakes. And I used to take these tutorial videos extremely seriously, and a 50-minute video would end up taking me 4 hours to make because I would redo everything all over again if I made a mistake. I'm no longer doing that. I'm just going to show my flaws and just make you, hopefully have you realize that I'm just a person just like you. Make mistakes, it's fine. But this is just the overall introduction. This is what I'm hoping you kind of know walking into the class. If you don't, please ask questions. You're going to hear me say that a lot at the beginning of the semester. Always ask questions. All right? I'll be more than happy to answer them. I can even meet with you if you want via Zoom or something like that. Just reach out and always ask questions. That being said, though, enjoy. Hopefully, you enjoy this semester with me. See you in the next video.